In the last lesson, we talked about row echelon forms, and specifically row echelon and reduced row echelon forms, and we hinted a little bit at how to get a matrix into a row echelon form. We looked at one example. What we want to do now is formalize that process into an algorithm meaning a repeatable process, a process we can perform over and over and over again to gradually move the matrix from its original form into reduced row echelon form. And the steps for that algorithm is what's called Gauss Jordan elimination. This is the Gauss Jordan elimination process. And we can follow this process over and over again. You'll notice here that the last step is go back to the second step and repeat steps 2 through 5. So what we're going to do is repeat steps 2 through 5 over and over and over and over until eventually the matrix is in reduced row echelon form. And the wonderful thing about Gauss Jordan elimination is that if we follow these steps exactly, they will turn any matrix into row echelon or reduced row echelon form every single time. Regardless of the original form of the matrix, we'll be able to get to the row echelon form that we want every time. So to see what this process looks like, let's use the system of 3 linear equations that we've used before. And we already know that if we transfer this system into a matrix, we get this matrix here. So we have the coefficients on x, 3, -1, and 1 down the first column, the coefficients on y, -2, -5, and 4 down the second column, and the coefficients on z, 1, 4, and -6 down the third column, plus the constants from the right-hand side, 2, 1, and -9 over here on the right side of the matrix, and we've got this augmented matrix here. So we're going to go through this Gauss Jordan elimination process to see how we can transform this matrix into reduced row echelon form. So the first step of Gauss Jordan elimination is always to pull out any scalars. This is an optional first step. We don't actually have to do this, but sometimes it'll make our calculations easier if this step is available to us. So what we mean by pull out scalars is if we have a constant multiple in any row of the matrix, we can go ahead and factor that out. We can pull it out to simplify the values in the matrix. So for instance, if the first row of the matrix here were 2, 4, 6, 8, we could pull out a common factor of 2 and reduce that row to 1, 2, 3, 4. If we look at our matrix, we don't have any factor that we can pull out of the row. There's no common factor here between 3, -2, 1, and 2, no common factor between -1, -5, 4, and 1, and no common factor between 1, 4, -6, and -9. We're only looking across a single row at any given time. So there's nothing we can do here to pull out scalars, so we can go ahead and say that that step is done. Our second step is to switch rows if the first row in the matrix starts with a 0. So if the first entry in the first row, which is going to be the entry in the upper left-hand corner of the matrix, if that's a 0, then you have to switch that row with another row that starts with a non-zero entry. This elimination process isn't going to work unless we make that switch. In our case, we have a non-zero entry. We have a 3 in the first row in the first column, so we don't have to do step 2. Next, we move on to step 3, and here we have a couple options. Our goal for step 3 is to get the pivot entry in the first row, and we want a pivot entry of +1. In other words, we want the leading non-zero term, the pivot entry, to be +1. So we could, for this matrix, we could divide through the first row by 3 in order to get a +1 here as the first entry. Or, alternatively, we could switch this row with maybe the third row, which already has a +1 as the leading entry. Because that way we'd already have our pivot and we wouldn't have to do any division. So let's go ahead and do that switch instead of dividing through by 3. That seems like it might be a little bit easier. So the third row will move up to the top and we'll get 1, 4, -6, and -9. And then we'll move the first row down to the bottom. We're switching the first and third rows. So 3, -2, 1, and 2. And our second row stays the same, -1, -5, 4, and 1. So now that we've switched these first and third rows, we have the pivot entry in the first row, and we have the pivot as a +1, which is what we want. So that's step 3. And then step 4 is to zero out the rest of that pivot column. So we want 0 entries here where the -1 is and where the 3 is. And the way that we're going to do that is by adding scaled multiples of this first row to the second and third rows to zero out these entries. So to get a 0 here in place of this -1, we can simply add the first and second rows together. That'll give us a 0 value. So we'll replace the second row with the sum of the first and second row. So let's go ahead and say that we're going to do the row operation. Row 1 plus row 2 is going to replace row 2. So that's what we're going to do here. And here's what that looks like. The first row will stay the same. 1, 4, -6, -9, and then we need to add the first and second rows. So 1 plus a -1 is 0, 4 plus a -5 is -1, -6 plus 4 is a -2, and -9 plus 1 is a -8. Now to get a 0 here in the third row where the 3 is, we'll take 3 of row 1 away from row 3. Because if we multiply row 1 by 3, we'll get a 3 here. 3 times 1 is 3. And when we subtract that from this 3, we'll get a 0. So our row operation is really going to be row 3 minus 3 of row 1 is going to replace row 3. So we'll do that next, and we'll say 3 minus 3 times 1 is 3 minus 3, or 0. -2 minus 3 times 4 is -2 minus 12, or -14. 1 minus 3 times -6 is 1 plus 18, or 19, and 2 minus 3 times -9 is 2 plus 27, or 29. So we get 29 there. So those are the two row operations that zero out the rest of the first column where we had that pivot entry in the first row. Now we get to step 5, which tells us to go back to step 2 and repeat the process again. So when we go back to step 2, what we're working on now is the second pivot. In other words, we already have the pivot in the first row, so we go to the second row and we look for the first non-zero entry. In this case, that's in the second column here, so we need to make this a pivot entry. Step 2 specifically tells us if that is a 0, and we have the opportunity to swap it with another row that has a non-zero entry in the second column, then we need to do that. In other words, if this -1 was a 0, but we have this -14 down below, then we want to swap rows 2 and 3 so that we have a non-zero entry here in the 2-2 position. In our case, -1 is already a non-zero entry, so we don't need to do step 2. We've got that -1 already. Now we need to make a pivot out of that entry, and we want the pivot to be a +1. So we'll multiply through the second row by -1. So that row operation is going to be multiply row 2 by -1 and replace row 2 with that value. The result will be 1, 4, -6, -9. That all stays the same. 0 times -1 is 0. -1 times -1 is 1. -2 times -1 is +2. And -8 times -1 is a +8. And then the third row will stay the same. So 0, -14, 19, and 29. And then we're going to go to step 4, which is going to be to zero out the rest of the second column. Again, we're going to do that by adding scaled multiples of the second row to the other two rows, the first and third rows. So to get rid of this 4, we want to multiply through the second row by 4, because 1 times 4 will give us 4 here, and then we can subtract that from the first row. So the row operation we really want to do here is we want to take row 1 and we want to subtract 4 of row 2 from that, and we want to replace row 1 with that result. So here, if we write that out, we'll get 1 minus 4 times 0 is 1 minus 0, or 1. 4 minus 4 times 1 is 4 minus 4, or 0, so we get the 0 there that we wanted. -6 minus 4 times 2 is -6 minus 8, which is -14. And then -9 minus 4 times 8 is going to be -9 minus 32, which is a -41. The second row stays the same, 0, 1, 2, and 8. And then the third row, to get rid of this -14, we want to add 14 times row 2 to the third row. So that row operation will be 14 times the second row plus the third row is going to replace the third row. So we'll say 14 times 0 plus 0 is 0 plus 0, or 0. 14 times 1 plus a negative 14 is 14 minus 14, or 0. That's the 0 that we wanted. 14 times 2 is 28. 28 plus 19 is 47, so we get a 47 there. And then 14 times 8 plus 29, 14 times 8 is 112. 112 plus 29 is 141. So we get 141 there. And then we get to step 5, which tells us to go back to step 2. Notice here that we're on the last row. The algorithm would tell us to switch rows if we had a 0, but we don't have any rows left to switch with, so we're stuck with that. We can't do step 2. Step 3 tells us to find the pivot entry. We would do that in the third row here by dividing through by 47. So we'll say that we're going to multiply row 3 by 1 over 47 and use that value to replace row 3. When we do that, rows 1 and 2 will stay the same. So 1, 0, negative 14, negative 41, 0, 1, 2, and 8. And then dividing through the third row by 47 gives 0, 0, 1. And then 141 divided by 47 is 3. And now all that's left to do is step 4, which is to zero out that last column with the pivot entry. Let's work on the first row first. So what we want to do to get rid of this negative 14 is to add to that 14 of row 3, because when I take 14 times 1, I'll get 14. When I add that to negative 14, I'll get a 0. So we want to say 14 times row 3 plus row 1 is going to replace our existing row 1. So let's start there. I'll get 14 times 0 is 0, plus 1 is 1. 14 times 0 is 0, plus 0 is 0. 14 times 1 is 14, plus a negative 14 is 0. And then 14 times 3 is 42, plus a negative 41 is 1. Now we want to zero out this position, the position 2, 3, where this 2 is. And we can do that by subtracting from this 2 times row 3. So this row operation will be row 2 minus 2 times row 3, and we're going to use that to replace row 2. So we'll say 0 minus 2 times 0 is 0 minus 0, or 0. 1 minus 2 times 0 is 1 minus 0, or 1. 2 minus 2 times 1 is 2 minus 2, or 0. And then 8 minus 2 times 3 is 8 minus 6, or 2. And we leave the third row the same. So 0, 0, 1, and 3. And we've now finished this Gauss Jordan elimination process. There's nothing left for us to do because the matrix is in reduced row echelon form. We have the identity matrix on the left side here. And remembering that this matrix represents this original system of linear equations, what we can say is that we have here a column for x, y, and z, and then the constants here on the right. So by getting the matrix into reduced row echelon form using Gauss Jordan elimination, we're able to see that x equals 1, y equals 2, and z equals 3 is the solution to this linear system.